Hello everyone, welcome back. Last class we stopped with solving a problem halfway. In a sense, we said there will be a flow through a duct 20 meter per second, and at the end of the duct I am suddenly putting a lid and making sure that there is no flow and it is done suddenly. That is the problem we were looking at, and we transformed that problem to this problem, where we said there is a velocity 20 meter per second coming in. Since it is right to left, I am going to say v equal to minus 20 meter per second, and here v equal to 0, and we found that the shock speed, or we said shock Mach number was 1.04, and towards the end of the class we iterated and came up with 1.04 as the final result. Okay. So, with this 1.04, if I want to go and find the strength of the shock, P2 by P1, I am going to pick from gamma equal to 1.4 normal shock tables. For this Mach number, I will get the strength to be 1.095. Okay. So, if I have a 20 meter per second flow in a duct and I suddenly stop it, I am creating a supersonic, I am creating a shock which is travelling supersonic, and it is going to have a strength of 1.095. So, the pressure in the duct is increasing by 9.5%, okay, and that is what is causing the flow to come to rest in the duct. If I want to find the shock speed, we know this formula already, I am just going to write it. I am putting minus 20 because V1 is minus 20. This answer happens to be 342.1 meter per second. So, what we are finding is the wave that is telling that there is a lid at the end of the duct is travelling at the speed of 342.1 meter per second. Okay. So, if I consider a case where I have a big tank with a thin tube through which I have that same 20 meter per second flow, and let us call it it is 1 meter long. If I have some case like this and it was having a steady 20 meter per second flow, and I just now at t equal to 0 put a lid at the end of the duct. If I did this, now when I look at this, it is going to cause a shock, exactly same situation, the 342 meter per second speed the shock is going to travel, and as it goes this way, it is going to make the flow behind come to rest completely. While initially there is a 20 meter per second flow this way, here V will be 0 after the shock. Okay. So, how long will it take for this flow situation to change fully in the duct? If I think about it, it is going to be 1 meter to be traversed by this whole shock. When the shock goes here, all the fluid inside is stationary. So, I am going to find that delta T, it will be 1 divided by 342.1. This is approximately 2.9 milliseconds, not meter per second, it is milliseconds. 2.9 milliseconds. Okay. It takes such a short time for 1 meter flow, 1 meter long duct to come to rest if the velocity initially was 20 meter per second. Okay. This is what you are going to see. Now, what will happen inside this duct? Here initially it is still considered to be really big, but still there is some velocity inside because gas from here is what was flowing out some time back. So, there was a velocity from every corner into this. If I draw streamlines, there will be streamlines coming like this, every streamline will want to go in through the duct. That is what it was initially. Of course, the velocity in the streamline will be very close to 0 at the wall and slowly increasing towards 20 meter per second when it comes in there. That is the actual flow field in this region. When the shock comes here at the exit, it does not stop, because if it stops here, what will happen? the flow from here will keep on going, it cannot stop suddenly, it will keep on wanting to go there. That cannot happen. So, this shock has to go and tell all the fluid that it can ever encounter that there was a problem there. So, it will keep on going in and it will go like this. It will start expanding to meet all the fluid elements possible. It is going to expand out, diffract out spherically, okay, and it is going to go out like this. Eventually, whenever it is crossing, by the way, it is the same shock, but now it is expanding and forming bigger area, it is processing much bigger volume flow rate, if you think about it, if it goes at the same velocity. But that is not possible for the shock because it has only fixed energy. So, what it will do is, as it expands, it has lesser strength. We will talk more about it when we are thinking unsteady flows, but anyways, when it is expanding, it is going to have lesser and lesser strength, which means it will cause lesser delta V, but it so happens that that is enough for this case. As I go this way along the streamline, the velocity is going to be lesser and lesser. When I come to this corner of the streamline, it is stagnant gas, right. If that is the case, then when the shock keeps on coming, the delta V required to stop this fluid is going to be lesser and lesser. Eventually, the shock becomes very weak and stops completely. Nothing more needs to be done. Okay. That is what really happens inside if I ever stop a flow. In case I did not stop it completely, but I had a small leak, then there will be a small velocity here finally. We are doing 1D analysis, remember. So, even if the leak is this way, I am going to consider it to be a small velocity this way. Let us say it is 1 meter per second leak, then this flow velocity is not 0, but it is 1 meter per second. So, the actual delta V that I am imposing is only 19 meter per second, that is all. Now, I have to go and solve the problem again. You will find that the Mach number of that new shock will be slightly less than 1.04, okay, because it does not need that strong a change, it needs lesser change, it will be lesser Mach number, that is what you will find. Okay. One more interesting thing I had to tell is this whole flow field was all subsonic, nothing was supersonic except the shock. Okay. What we are seeing is, even if the flow is completely subsonic, very low velocities, okay, it can be considered as an incompressible flow problem, right. If it is just 20 meter per second, it can be considered as an incompressible flow problem. If you think about Mach number 20 divided by 350 meter per second, it is very, very small, okay, it is less than 5% in Mach number itself. We can go all the way up to 0.3 Mach number for compressibility effects, we said. So, it will be a very, very small number, but still 0.07 kind of Mach number will be what you will get roughly, okay. That is extremely small, but still when the flow is unsteady, I am suddenly changing something in time, right. At t equal to 0 onwards, there is a lid. If that is the case, then we are finding that there is compressible flow happening inside even when the velocities are extremely low, okay. This is the main point I want to drive through this whole course. I want to say that when the flow is unsteady, compressible flow field can happen anywhere at any velocities, okay, because the gas can adjust only through compressible effects, okay, only through compression waves or expansion waves, which are all compressibility related effects. That is the only way a fluid can communicate from one point to another. The only way that the fluid inside this tank can know that there is a wall suddenly appearing is through this shock, and that is a wave that is going through, it is a pressure wave, it so happens it is a high pressure wave. Now, I can have a straight opposite problem if you want, this is just going beyond my notes. If I have a straight opposite problem, I am having a tank filled with some high pressure gas, I suddenly open this lid, now there will be a flow created. Why? This is a high pressure region, this is a low pressure region, outside is let us say atmospheric, inside is let us say very high pressure. Then at t equal to 0 I open it, the actual velocity of final steady state may still be 20 meter per second, okay. But the process of accelerating this stagnant gas inside the duct is happening through expansion waves going this way, which will tell that there is less pressure there, so everybody move that way, that is the information that is going that side, okay. It is going to go into the duct and again it is going to diffract out, expand everywhere and tell that you people move a little bit slowly, but that is enough, okay. That kind of information is going all the way out. That is how you create this particular flow field. Okay. This is beyond the notes, we have to go back to expansion fans later and talk about it again. Now, we will go to another problem. This is from continuing with the same numbering, it is problem E. D was the previous problem. E. Now, I am leading to something which I want to go to in the next lecture. So, what I am going to have is a leak free piston in a duct. There is no leak across the piston, and I am going to say at time t equal to 0, the whole gas in the region is all at rest, and suddenly it is moving with 20 meter per second. It is moving very low velocities, it is not very high. Okay. But when this is happening, I am going to say what will happen, there will be a shock created, because suddenly this gas is going to tell there is some problem here, we have to run away from here. That information is going through with a shock. It is like the snake is moving or whatever, something like that, that kind of information. If you want more, it is like some bomb is exploding or something like that. Everybody wants to get away from this region. V equal to 0 here, V equal to 20 meter per second here. And of course, we do not know this Ws as of now, the speed of the shock. We do not even know the strength. All we know is A1, we will keep the same temperature 300 Kelvin. So, A1 is 348.2 meter per second. Okay. If I go through the whole set of formulation, I will get to this. I wrote this last class, so I will go from here. I will have this formula. You will derive it if you go through the whole whatever way we solved it till now. U2 minus U1 equal to V2 minus V1. From there you substitute everything in terms of Mach number, you will get to this form. Okay. Now, we just want to solve this problem. It is the same problem, we just do not know the strength. So, I have to start guessing M1. Okay. I am given delta V. It happens to be V2 minus V1, 20 minus 0, it will be 20 divided by 348.2. So, I am having M1 minus M2 square root of T2 by T1 minus 20 by 348.1 equal to 0. If you go back to the previous problem, the last class towards the end, we solved this exact same equation. It was exactly the same 20 by 348.1. Okay. When we are solving the same equation, math will give exactly same answer. I do not need to solve this problem again, but if you want, you can solve this by iteration and you will get exactly the same M1 equal to 1.04. Okay. We will see the link now. Okay. Well, how are these two problems the same? Not very difficult to show. But I want to tell one more thing just from looking at this expression. It so happens that if I guess a M1, I know M2 and T2 by T1. They are all related to shock strength. But this term is related to the change that is happening in the fluid. One set of terms is related to shock strength that is going to cause the change, and this is the actual change that is caused. Okay. If I tell that the delta V that is needed to be created in the flow is some value, and the speed of sound for the original gas, the incoming gas for the shock, happens to be A1. If I give this value or the ratio, actually what matters happens to be the ratio really, not the values. If I tell you for a particular T1 and gas, if I want to make a delta V of so much change, I do not care whether V1 is 100 meter per second or 0 or minus 2000 meter per second. If I tell you that I want to change the velocity by 20, the shock that is needed will be 1.04 if I assume A1 is 348.1. Okay. So, that is what is important, that is what I am going to see from here. This is a nice way of telling that if I want to make a change, for every change there is a particular shock strength that is needed in the flow field, and that is related to speed of sound in that medium in which I want to make the change. Okay. That is what you are going to see in this whole thing. But I can go and solve this whole problem, I do not need to. The only difference will be Ws. Okay. from problem D to problem E, Ws now is going to be V1 minus U1, where V1 is 0. Okay. So, it will just be minus of U1, which is equal to minus of minus M1A1. Remember, we used U1 as minus M1A1, so that minus gets cancelled. So, this number will come out to be 1.04 multiplied by 348.2, which is 362.1 meter per second. Okay. This shock speed is different. Even though the shock strength, the Mach number and the P2 by P1 are the same, the shock speed is different. That is the only change you will see. Okay. Speed with respect to the reference frame is different, velocity depends on reference frame. So, since the reference frame is different, I am going to have a different velocity. We will see the connection between these two problems right now. Okay. In problem D, we had a case where there was a duct, there was 20 meter per second flow this way, there is a shock going this way, and it is, oh, the shock is going the other way, sorry. Shock is going to the left, and here V equal to 0. This is the problem we saw, and in problem E, whatever we just solved, the problem is there is 20 meter per second flow coming, and that is the effect of this shock moving like this, and V equal to 0 here. It so happens that in both the cases delta V happens to be plus 20 meter per second. Okay. That is why you are getting the shock strengths to be exactly same, M1 and P2 by P1 are the same. Okay. Now, how are these two problems the same? That is the only thing I have to see. I will write the velocity values for the speed of shock. For problem D, it was 342.1, and in this problem it is 362.1. Okay. Now, if I say, it is very difficult to look at it this way, I will just transform this problem to our way of looking at it. I will transform this to looking from the other side of the board. V equal to 0, shock is going to the right and velocity is against it. If I have a case like that, I have just transformed this exact problem that way, it is nothing wrong, I have just multiplied with -1 for the whole system. Or I can say that instead of looking from this side, I am looking from the other side of the board, then it will look like this. So, now if I have a situation where I have an observer, as of now he is stationary to observe this particular problem, I am going to now say that he is going to move this way with 20 meter per second. If he is moving this way with 20 meter per second, what will he observe? He is going to say that this fluid is stationary with respect to him, because they are both going parallel to each other at the same velocity. Okay. And this fluid, which was originally 0, will now be seen as coming this way with the same velocity. Okay. And this is going faster, but I am going this way also. So, only the relative velocity will remain, that will be 342.1. Whatever I have just done, because this guy is now moving, you will see that it becomes this problem. Okay. That is why you are getting exactly same M1, because it is just a reference shift from this problem to this problem. That is the only change we had. Just reference frame was moving with 20 meter per second different in these two problems. That is the only way you will finally conclude. That is the only thing that is happening in this flow. This is the link between problem D and problem E. The same thing we discussed, and we said that problem A and problem B had the same kind of link, only the reference frame was shifted by 20, I believe that was 100 meter per second. That is the only difference there. Okay. Now, this duct and a piston, actually I will start from the next page here. Okay. I have this duct and a piston arrangement, and I am going to say it is starting to move at t equal to 0, and after that there is shock, and velocity behind is same as the velocity of the piston. Okay. If I wait long enough, what will happen? The shock would have gone well past into the duct, and what we will see will be just a steady flow where the fluid here has having the same velocity as the piston, which is what our incompressible flow world will be talking about all the time. But if I am interested in the unsteady phenomenon from t equal to 0 onwards, then there will be a compressible flow field happening there, there will be a shock that will be created, and it will be going at supersonic speeds. Okay. All that is happening in there. I am keeping on repeating this, unsteady flow will mean there will be compressibility. Okay. Keep remembering that. Now, if I think of this problem like this, and I call this is my x coordinate, I want to plot things x versus t. Let us say I want to plot this. Let us say at t equal to 0 the piston was here and it was at rest. Okay. And just when that moment any t that is greater than 0, it is going to be going with a constant speed. Constant speed will mean dx by dt is a particular value. So, it will have one constant slope. Let us say this is my piston. This is the trajectory of my piston. What is happening? As time increases, the piston moves this way. Okay. That is what I am seeing. Now, I want to plot the location of the shock on this plot. At time t equal to 0, there was no shock because there is no change, but immediately after that the change happens from the piston and it moves away from the piston. So, and it is moving at a constant speed, which was what, 362 meter per second. So, that is going to be something like this. It is supposed to be a straight line, I have drawn it slightly curved, imagine it is a straight line. Okay. And this is your shock. Okay. Now, this will help you understand 2D flows automatically, okay. But we will go to 2D flows today towards the end of this, if not next class beginning. If I want to look at say a particular particle of fluid which was sitting somewhere, let us say I will pick a fluid particle that was originally sitting here at t equal to 0 when the piston was actually sitting here. If I pick such a case, piston initially was here at x equal to 0 and the particle was at x more than 0. It will not move till the shock crosses this point, which means it will be at the same x for a set of time values. After that, it will have a speed which is same as piston velocity. So, it will have a slope on this thing parallel to this piston slope, that will look like this. Okay. If I pick another point somewhere here far away, that is going to be somewhere here, and it will remain constant till the shock reaches that. Let us say that happens at this time. After that, it is again going to go with the same velocity as the piston, so it will again be parallel to the piston. This is what happens. If I look at one special thing, at any particular time after they have been processed by the shock, these two particles have come closer. The delta x between them is lesser now than before. Okay. This is related to the gas getting compressed. Okay. Initially the gas was occupying this big volume, now it is occupying lesser volume. That is what has happened here. Okay. This is the effect of compression, and depending on the change delta V, it may be very strong compression or very weak compression. If the piston moves very fast, I will draw another picture very quickly here. If the piston moves very fast, the shock will be very strong, and you will find that the delta x at any particular time will be much smaller. If the piston moves fast, what happens? The delta V is very strong, the M1 will be very strong from that formula we just looked at today. Okay. I am going to look at this from here this much volume is now becoming this small volume. Okay. If I had this big separation initially from this and this, final separation may be this, just that distance between them. That is also going to happen. This is related to compression. Even when I am having piston moving at subsonic speeds, it is going to cause a shock, which is a compressible flow field phenomenon. Okay. That's the thing I just want to keep on driving whenever there is unsteady flow. This is an unsteady flow field, moving shock. Okay. It is an unsteady flow field. And that is why all this is happening. Immediately after this, next class onwards, we will be talking steady gas dynamics, where we won't have anything moving. It is all with respect to some fixed stuff. Shock is going to be fixed with respect to my reference frame. That is also going to happen. If I waited long enough, these shocks, the unsteady phenomena, will go all the way up to infinity into the gases. All the gas in the flow field will know that there was a change, and only after that, if I look at the flow field, there will be no compressibility effects, and it will look like our ordinary subsonic flow field. Okay. Which we saw in the previous problem. Problem D, we said if I wait for more than 3 milliseconds, the duct will have subsonic flow field steady state. Okay. Within that 3 milliseconds, if I have a very high speed camera, I will see that shock moving. Okay. That is also going to happen. Now we will go look at a new problem. This is probably the last problem I will solve, because I want to make you familiar with solving for entropy also in a moving shock situation. So, I am going to pick a case. I am going to pick the same case as what we solved before, problem A, so that it is easier. I will just solve only whatever is needed. I was given P2 by P1 in problem A to be 4.5, which immediately gave me my M1 was 2.0. Okay. And we had T1 equal to 300 Kelvin, P1 equal to 1 bar, gamma equal to 1.4, A1 equal to 348.1 meter per second, and we found that time we were interested in finding V2, which was 435 meter per second. This is what we were interested in that time. We solved this and we said that is the answer. Now we want to go beyond this. Okay. We want to solve for the entropy change across this. Before that, I want to solve P02 by P01. Only after I solve this, I can solve entropy change anyway. So, we will solve this. Okay. P02 by P01. Just for an instance, let us say I will put a parallel the shock fixed coordinate system. Shock fixed coordinate system, my U1 was minus 696.4 meter per second, and my U2 was minus 261 meter per second. This is what we had. This is all same problem, I am just repeating it. If I have such a case, and for this problem M1 equal to 2 case, I go to shock fixed coordinates, right. So, I can directly go to normal shock tables, gamma equal to 1.4, and I will get P02 by P01 is 0.721. Of course, we already saw that in a normal shock P0 drops, that is what you are seeing here, and we know that T02 by T01 equal to 1. This also we know from normal shock tables, normal shock, not really tables really. Delta S by R was given to be log of P01 by P02, which is log of 1 by that number 0.721. It happens to be 0.327. Happens to be 0.327. This is one way of solving. Now, depending on what units of S I want, per mole or per mass, we did that kind of exercise already. Per mole or per mass, depending on that, I will use the correct R here, 8.314 or 288.6, whatever needed. we will not deal with that, I just want to look at the ratio right now. Now if I want to solve this in the moving shock problem, I have to go and do that cyclic ratios. I will do it this way because these are the numbers that I can get from my tables. Okay. And this is coming from M2, my induced Mach number for the flow behind the shock in the moving shock. Okay. This is equal to V2 by A2. We know that V2 was 435 and A2 also we calculated based on T2 by T1 and 348.1. A2 happens to be 452.2 and M2 happens to be 0.962. That is the number I am having for calculating this. Now I will go and find from my isentropic tables for this Mach number gamma equal to 1.4, what is the P naught by P value. Okay. Then I can get to this ratio. P2 by P1 I am getting directly from my Mach number M1 equal to 2. Actually we were given 4.5 directly, I will just use 4.5 here. And P1 by P01 is given by Mach number of the initial flow based on V1 by A1. V1 was 0 for us. So M1 is 0, which means P01 equal to P1. It is stagnant gas, it is not moving. Okay. So that is going to be 1. So if I put all of them together, P02 by P01, in my tables it so happens that they give P by P0 for isentropic tables. So I am going to write it as 1 by 0.552 because that is the number I get from my tables into 4.5 into 1. This number happens to be 8.15. Okay. So we are getting a P02 by P01 as 8.15, while P02 by P01 in shock fixed coordinates was 0.721. This is less than 1 and this is very high compared to 1. Okay. That is what you are getting. Remember this, it is not yet done. If I go and calculate delta S by R based on this formula, it will be wrong. Okay. You have to use the appropriate formula. I told this that time also. Right. We will go and use the correct formula later. The correct formula, we were deriving this some time back when we wanted to find delta S by R, and then we simplified it one step. I am taking one step back in that. We had a formula like this. We had a formula like this when we were doing fixed coordinate normal shock. When we did that shock fixed normal shock, we said that T02 equal to T01 there, and we made this 1, and so we had log of P01 by P02, which is the formula we used for shock fixed coordinates. Now for this problem we know T02 will be more than T01. We saw plots last week actually. Okay. Yeah, I think 3 classes, 2 classes behind, whatever. And so we know that this is more than 1, it is not equal to 1. So I have to take this also into account, then only you will get correct answer. So now we have to do that for this problem. We will go to the next section. We want to find T02 by T01. Same procedure, cyclic ratios. And of course, this is going to be equal to 1 because my gas is stagnant based on V1. The remaining things I will just put numbers directly, you know how to calculate, same as what we did for pressure. This is the number I got. Okay. I could have made it 2, I just wanted to keep it whatever my calculator gave. Okay. So now my delta S by R comes out to be log of 1.999 to the power gamma by gamma minus 1, which we know is 3.5. If you do not know, you should know it. Okay. For gamma equal to 1.4, this is 3.5. P01 by P02, which is 1 by 1.8, 1 by 8.15. This answer happens to be 0.326. Okay. Now let us say I do not want to use this complicated T naught based formula, I directly go and use delta S by R equal to gamma by gamma minus 1 log T2 by T1 minus log P2 by P1. Where did I get this? This is same as delta S equal to Cp log T2 by T1 minus R log P2 by P1. It is the same thing, I just took the R out of here. So, this is the formula. Now, I know T2 by T1 for the shock, I know P2 by P1 for the shock. I can find this way also. Ideally, I can substitute all the numbers, you know all the numbers, I will just substitute it. This also gives me 326, exactly the same answer. Both are exactly the same formula, it is just one way or the other, both should give the same answer. Now, I want you to look at the previous thing we did here, where we had a shock fixed coordinate system, and here we are having delta S by R 0.327. This is approximation error, it should be same 0.326. Okay, it is just approximation error, it should have been 0.7215 or something, then you will get to the correct answer, something like that. Okay. I just missed that 4th decimal, but anyways, these two numbers are same. Okay. What this means is entropy change for my fluid, whether it is moving shock or static shock, stationary shock, it does not matter, I am going to get the same entropy change for the gas. Okay. Even though my P02 by P01 or T02 by T01 are very different. Okay. Very important information, you have to note it. Okay. We have to see the reason for this. Because entropy is a state property of the gas, that is the main reason. Okay. The gas was initially something at state 1 and now it was processed by the shock and now it went to state 2, and that delta S is just S2 minus S1, that is the difference you are going to get, and it does not care whether the observer was moving or not with respect to the shock. Okay, that is the difference between these two problems, right. If I have my observer moving along with the shock, then it will look as if shock is stationary with respect to the observer, that will become your shock fixed coordinate system. Or if my observer is stationary with respect to my V1 gas, then it will look as if the shock is moving. That does not matter as far as the gas state is concerned. The state of the gas is say same T2 and P2 from T1 and P1. So, the delta S for the gas on my state diagram should not change, it will change only in the reference frame, that is the only thing, that is what we are going to look for. Okay. So, how will I say this? The first thing I can say directly is it is a state property, so it does not depend on reference frame. Why do P0 and T0 depend on reference frame? Because P0 and T0, both of them have, okay, I will do individually. P0 has pressure energy and kinetic energy of the gas, pressure energy and kinetic energy. T0 has enthalpy and kinetic energy of the gas. It so happens that the kinetic energy part is what is going to cause trouble. The kinetic energy depends on velocity and velocity depends on reference frame. Okay. And that is what is causing all this trouble. Kinetic energy depends on reference frame because velocity depends on reference frame. Okay. But overall the gas is processed by some particular shock that is moving, and that is going to experience some particular state change, and that says my delta S cannot change anymore. Okay. It is just the same value irrespective of what reference frame I am on. Okay. Now, from here the next step what we want to take is go to 2D shocks. We have been doing 1D shocks till now, one dimensional. Okay, we said 1D flow field, quasi one dimensional, whatever we did till now. Now we are going to move on to 2-dimensional flow. Okay. Before I go and show something, I will just give you a video that we took from the lab. Let us go to the screen, and here we have, actually it is a bolt, okay, it is actually a metallic bolt. You can see the threadings on it. After that it was ground to become a wedge, okay, it looks like a wedge shape here. Now it is flat surface here and here. It is still having the curvy surface on the side, in fact it has the threading on the side also, okay. And now this is kept in a approximately Mach 2.0 flow field. It is actually Mach 1.98 or something, it is roughly Mach 2 flow field in our lab, and you are seeing this a window through which we are seeing what is happening in front of the flow, in front of this body. There are some scratches on the wall, ignore that. Now I will start it, you will see the flow starting to happen. Okay. Suddenly you are seeing there is a nice line coming like this and on the other side, and they are continuously increasing the pressure jump across is going to be higher. Let us not worry about that part currently. You are getting a clean flow field now, it is having a fixed line of jump in pressure. You do not know how you are seeing this currently, ignore it, we will go deal with how to visualize shocks or expansions in a flow field later. But what we are seeing, I will run it again, what we are seeing is here there is a sudden jump in pressure, and after that there are some weak lines similar to whatever we saw here, some weak lines. Those weak lines actually are coming from, I told no, it is a bolt, the edge of the bolt is disturbing the flow, and that disturbance is what we are seeing as, if you want to call it, Mach cones along the flow. The flow field is going to come straight, is going to turn along the bolt and go out from here. Let us not worry about what happens at this corner, it has to turn back and go. What we are seeing is those extra lines that coming this way. Now I will go to the next case where I am having roughly a spherical body sitting in that same tunnel, okay. And again we are starting the flow, you can see the vibration of this body, its flow is starting, okay. So let us say it is forming anyway, okay. When the flow field forms here, actually you are seeing that the body is having an optical illusion, it looks like it is more flat, that is optical illusion because of density gradient in that region, okay. Light bends in density region, density gradient. But other than that, you are seeing that there is a thick line here which is what they call a bow shock, okay. This line is what they call a bow shock, okay. This line is the bow shock. Now after that there is some set of lines here very weak, which we will not worry about right now, we will deal with it when it is time to look at it, okay. So that is the end of my video session. We will come back to what we want to say on the board next. If I had this piston and cylinder we talked about, and well, actually I have it on the board here, let us not go anywhere else. If I look at the flow field which we saw before the first video we saw today, it looked like this. I will draw it here and then I will compare it with that picture. I had a wedge that was something like this, and there was a supersonic flow over it, and it created a thick line like this. We talked about all this before, okay. Now I am going to say that when this line is created, the flow incoming is straight up to this point. After that, this wave that was running from the tip is going into the flow like this, normal to this, and it is now able to see this streamline is now able to see that there was a change occurring here. Now because of that, this flow will turn and go along this line. that will start happening at this point. Okay. So, if I look at another streamline, it is going to do something like this. I will pick another close to this streamline somewhere here. They are parallel, and when they go out again they should be parallel. Similar to that picture which we had here, there are two streamlines coming here, they are going to meet the shock line and then they are going to turn, go along the wall. Same thing happening here, parallel initially, and they are going parallel to the wall. If I look at it, the streamlines have come closer, this distance is less than, this distance is less than this distance, the streamlines have come closer, okay, which is what tells me that the fluid element which was sitting inside between these two, considering this as my stream tube, now my stream tube has gotten crushed, which is what is my compression, it has got compressed. Okay. So, basically this is actually sitting as a shock here, this is what they call as a oblique shock. It is not normal to the flow, but it is slanted, it is oblique. Okay. The word oblique means slant anyway. Okay. It is going to become oblique shock. And now from next class onwards we are going to look at oblique shock, and I will bring an animation next class where I will show that this analogy with this flow can be easily seen if you look at that particular analogy. Okay. It will be very easy to see that particular animation. We will stop at this point. I could have brought the animation today, I just did not, thinking it will take more time. So, we will start with animation and then move on to analysis of oblique shocks in the next class onwards. See you people next class.